That fellow standing behind me is Bob Lindy. He's one of the best carburation and ignition men I've met in a long time. Weekdays from 8 to 5, he's the tune-up expert at Stateside Motors. 2 nights a week, you'll find him right here at the local high school teaching an adult education course on carburation and ignition. I'd like to have you all hear what he has to say on the subject of ignition system analysis.
Thanks, Tech, and feel free to sound off if there's anything you want to add to what I have to say. You can't do an expert job of diagnosing and correcting ignition system problems unless you know what the ignition system is supposed to do, why it's supposed to do it, and what happens when it doesn't do what it's supposed to do. What does the ignition system do? It boosts the low voltage available at the storage battery to the high voltage needed at the spark plug to fire the air-fuel mixture in the combustion chamber. But that's only part of the job. The ignition system must also control the timing of the spark for the best performance under all operating conditions. The ignition system is divided into 2 distinctly separate circuits. The low voltage or primary circuit starts at the battery and includes the ammeter, ignition switch, ballast resistor, primary winding of the ignition coil, the condenser, the distributor contact points, and the necessary connecting wires. The secondary, or high voltage circuit, begins at the secondary winding of the ignition coil and includes secondary ignition cables, the distributor cap, the rotor, and the spark plugs. Once you understand the function of each of the ignition system components, as well as the possible malfunctions of these units, you'll find it a lot easier to diagnose ignition troubles. So let's go through the system, 1 unit at a time. The battery is the source of electrical power for cranking the engine and operating the ignition system. It also provides the power for the lights and electrical accessories. There are 4 common causes of battery trouble: a cracked case or cover, continued undercharging or overcharging, neglected maintenance and service, and an undercapacity battery. Whatever the reason, a battery in poor condition will cause starting and ignition problems. Battery testing and service is the subject of another session in this series. However, the battery should be inspected and tested as part of every tune-up or ignition job.
I'd like to put in a word here. Don't take battery condition for granted. There's no excuse for not testing. With a wide variety of battery test equipment available, the only question is, which one to use? What's your choice, Bob?
I stick to the hydrometer and specific gravity readings as the logical starting point, Tech. If the specific gravity of all cells is 1220 or higher, the state of charge is okay. If there's less than 25 points difference between cells, the battery is probably serviceable. Next, let's consider the coil. The ignition coil increases the low voltage available at the battery to the high voltage needed to jump the gap at the spark plug. Under actual operating conditions, the output voltage is determined by the amount needed to cause the spark to jump the plug gap. This varies from about 5,000 at idle to about 15,000 volts at higher speeds. However, under open circuit conditions, the secondary voltage may go as high as 25,000 volts.
And let me warn you, don't crank the engine with secondary coil cable disconnected. The high open circuit voltage will damage the coil. If you want to keep the engine from starting when it's cranked, disconnect the primary wire from the distributor side of the coil. Using a jumper to short out the primary can overheat the coil. Disconnecting the hot coil lead can cause fireworks.
Speaking of coil connections, the coil must be connected for the correct polarity. Battery to the plus terminal, distributor to the minus terminal. Here's why coil polarity is so important. The spark jumps the gap at the plug more easily when the electron flow is from the hotter center electrode to the cooler ground electrode. Reversing the coil leads causes the spark to jump from ground to center electrode, and this may require as much as 40% higher voltage.
Here's a clue to wrong polarity. If you're using an oscilloscope and the pattern's upside down, check the primary connections at the coil. Either these connections are reversed or the oscilloscope isn't hooked up right. Actually, there's no excuse for incorrect connections at the coil, but it does happen.
I'm afraid it does, Tech. Now, a special ballast resistor is connected in series in the primary circuit. It limits voltage at low speeds but allows an extra margin of ignition voltage for high-speed driving. Limiting low-speed voltage increases ignition contact life and lowers coil operating temperatures. Don't try to cure an ignition problem by using a bypass or jumper around the ballast resistor. You may get a hotter spark at low speeds, but the ignition points won't last very long. On the subject of ignition spark intensity provides a quick clue to possible ignition troubles. Simply remove a plug cable from one plug, stick a conductor into the terminal, and hold it about 3/8 of an inch from a good ground. Crank the engine and observe the spark. If the spark is very weak or won't jump a 3/8 gap, I know I have ignition trouble, and I check it out starting with the primary circuit. On the other hand, if the spark is good and jumps the gap easily, the basic ignition system is probably okay. If the complaint is hard starting or amiss, I check the spark plugs, secondary cables, and the fuel system. Next, let's tackle the condenser. The condenser does two things. It helps the coil develop higher voltage because it speeds up the collapse of the magnetic field when the ignition points open, and it reduces arcing across the ignition points.
The only sure way to test condenser capacity is with a condenser tester. Now, let's hear what Bob has to say about circuit resistance.
High resistance anywhere in the primary circuit will reduce voltage available and cause ignition problems. I guess every technician has his own pet way of checking circuit resistance. The important thing is to make sure both the ignition start and the ignition run are okay. Here's how I go about that. If the battery is charged and voltage at the ignition switch side of the ignition coil is 9.5 volts or higher when cranking the engine, the start part of the ignition circuit is okay. If cranking voltage is lower than 9.5 volts, the trouble is probably in the starting motor, or it is high resistance in the primary ignition circuit. To check for resistance between the battery and the ballast resistor, connect a voltmeter across the circuit from the battery to the ignition switch end of the ballast resistor. Also, disconnect the voltage regulator lead to eliminate current flow in that circuit. With ignition on and points closed, the voltage drop shouldn't be more than about 0.4 of a volt. If the drop is greater than that, leave the voltmeter hooked up and check out the connectors in the circuit. The easiest way to quick do this is to wiggle each connector and watch the voltmeter. If the needle jumps, you've located a trouble point.
Don't forget the ignition switch. Turn the switch off and on several times. The meter should come back to the same reading each time. For good measure, wiggle the key a bit. This shouldn't make the voltmeter needle jump.
That's an old trick, Tech, but it's a good check for a faulty switch. Next on the program is a distributor. It has two basic functions: to close and open the primary circuit so a high voltage will be induced in the ignition coil and deliver the high voltage to the spark plugs at the right time. Let's consider ignition timing. Ignition timing requirements depend upon engine speed and the load on the engine. And of course, engine speed and load change every time the driver moves the accelerator. That's where the centrifugal and vacuum advance come in. As engine speed increases, the time available to burn the mixture in the cylinders decreases. The centrifugal advance mechanism in the distributor automatically adjusts timing so that the mixture is ignited earlier. This gives the mixture time to burn completely during the power stroke.
The centrifugal advance curve on our distributors is carefully calibrated in production. However, if there is any reason to question the operation of the centrifugal advance, check distributor operation using a reliable test bench. Now, it's a fact that under part throttle and light load conditions, the air-fuel mixture isn't as highly compressed. The fuel particles aren't packed as tightly together, and it takes longer for the flame to travel from one particle to the next. As a result, under part throttle and light load conditions, the combustion process is slower, and the mixture must be ignited sooner so that all the fuel will be burned before the end of the power stroke. The vacuum advance takes care of this little detail. And if someone out there will take care of that little detail of turning the record, Bob will tell you how the vacuum advance unit works.
The vacuum advance diaphragm is linked directly to the breaker plate. Vacuum acting on the diaphragm rotates the breaker plate against the direction of cam rotation. This causes the breaker points to open sooner, so the spark is advanced. For example, on a level road under part throttle cruising conditions, vacuum is high, and this advances the spark for maximum efficiency and economy. And remember, this is in addition to the centrifugal advance provided at cruising speed. If the throttle is suddenly opened wide, vacuum decreases, and the spring-loaded diaphragm quickly moves the breaker plate back toward its original position. This is desirable because at open throttle the mixture is more highly compressed, burns faster, so less spark advance is needed. To eliminate vacuum advance at idle, the vacuum source for the advance unit is a port located in the carburetor throttle bore just above the throttle plate when it's closed.
And that suggests a warning. If engine idle is higher than specified, the vacuum advance port will be partially uncovered, and you'll get some unwanted spark advance at idle. To make matters worse, higher than specified idle speed also causes some unwanted centrifugal advance. So if carburetor idle mixture and speed aren't right, ignition at closed throttle will be advanced, and the engine will tend to race when the throttle is released. Any other tips, Bob?
Just a couple, Tack. If the diaphragm in the vacuum advance unit is punctured, both economy and performance will suffer. To test the diaphragm, apply vacuum to the advance unit. I find the easiest check is to apply mouth suction to the inlet and see if the diaphragm moves the breaker plate and holds without leaking. Be mighty careful how you go about disconnecting or connecting the vacuum advance line to the vacuum advance unit. A careless yank or push can spring things enough to affect the calibration of the vacuum advance unit. Before checking or adjusting basic timing, remove the vacuum line from the vacuum advance unit and plug the end of the line. Disconnecting the vacuum line is the surest way of making sure unwanted vacuum advance doesn't give you a false basic timing indication. After setting basic timing, I speed up the engine and watch to make sure the timing advances as speed increases. This doesn't take the place of bench testing the distributor, but it does assure me that the centrifugal advance is working. Next, let the engine idle. Reconnect the vacuum line and watch the timing marks. There should be no timing change. If the timing advances, I recheck carburetor mixture and idle adjustment to find out why vacuum advance is coming in at idle.
On today's engines, it's very important to set timing exactly to specifications. A few years ago, most engines would tolerate a certain amount of fudging to compensate for fuel octane and other variables. On current models, use the recommended fuel grade and set the timing right on the specified button.
Here's something that's sometimes overlooked. Because point gap and dwell affects timing as well as secondary voltage, timing must be rechecked whenever point gap is adjusted or changed. If contact point gap is too wide, the points open sooner, so ignition timing is advanced. Besides, dwell and secondary voltage are decreased, causing a miss at higher speeds. On the other hand, a narrow point gap causes point bounce and results in rough engine operation at lower speeds and missing at higher speeds. Play it safe. Double check yourself after installing points by taking a dwell reading to make sure you're within specs. And that brings us to the distributor cap. The distributor cap and rotor are simply a sequence switch which completes the secondary circuit to each of the spark plugs in the correct firing order. Corroded terminals or cracks are the most common kinds of distributor cap trouble. A visual inspection will usually disclose these conditions. However, carbon tracking and hairline cracks can be tricky conditions to spot. As a matter of routine inspection, Try to wiggle the rotor with your fingers to make sure it fits tightly on the distributor shaft. A visual inspection is all that's needed to spot a pitted or burned rotor.
I know that spark plug cables come next in the secondary circuit, but I think it'll be easier to understand cable problems if we cover spark plugs first.
I'll buy that, Tech. The spark plug provides the gap across which the high voltage in the secondary circuit can discharge a spark to ignite the fuel-air mixture. The heat range of a spark plug depends largely on the length of the insulator tip. A spark plug with a long tip transfers heat to the cooling system slowly, so it's called a hot plug. A short tip gets rid of heat quickly, and it's a cold plug. Just be sure and use the recommended plug. Now, if you'll bear with me, I want to cover a rather technical fact about plugs and ignition voltage. An ignition system in good condition can produce more ignition energy than is actually needed to provide good ignition. This provides an extra margin of ignition output to ensure good performance. However, this extra electrical energy would cause radio interference and would shorten plug life if it weren't controlled or suppressed. That's why special radio-type ignition cables are used instead of cables with ordinary copper wire. The resistance built into these radio-type secondary ignition cables suppresses the extra energy that isn't needed for ignition. This reduces radio interference caused by the ignition system and increases plug life. Even so, it is normal for plug gap to increase about 1/1000th of an inch every 1,000 miles of driving. Plug electrodes also become rounded, and this, in combination with gap growth, increases the voltage required for good ignition. That's why plugs must be reconditioned or replaced periodically. Visual inspection of the spark plugs provides valuable clues to engine performance problems which may or may not be caused by the ignition system. The plug condition pictures in the service manual tell this story better than anything I could say.
Many perfectly good spark plugs are scrapped by mechanics who don't know how to use a compression-type tester. Here are a few facts about testers worth remembering. Under actual operating conditions, plug tip temperatures average about 1,000 degrees. And as was pointed out earlier, a spark jumps more easily from a hot electrode. In the plug tester, the electrode is at room temperature. In the engine, the air-fuel mixture provides a much better electrical conductor than the dry air found in a plug tester. In addition to this, under operating conditions of the engine, ignition usually occurs before the piston reaches top dead center, before peak pressure is reached. So the plug doesn't have to fire at maximum compression pressure. Here's how you should use a compression-type plug tester. Compare the maximum pressure at which a new plug will fire in the tester with the pressure required to fire a plug that has been cleaned, electrodes filed, and gapped. If the used plug will fire at a pressure that's as much as 30% less than a new plug, it will still provide good ignition.
If a spark plug fails to fire because of other ignition system problems, the condition may be temporarily helped by installing new plugs. However, this won't correct the basic trouble, and the customer will soon be back with the same old problem. Before I wind this up, I want to warn you about some spark plug cable problems. If they aren't properly routed, they'll be unnecessarily subjected to oil spillage, engine heat, and mechanical damage. In addition, current flow through the ignition cables sets up a magnetic field which is strong enough to cause crossfiring if the cables aren't properly routed. Here are 3 things that will minimize crossfiring, or as it's sometimes called, induction firing. Adjust spark plug gaps to specifications to reduce the voltage required to fire them. Route the cables properly and mount them in their brackets. Never tape or bind cables together in a bundle. It's particularly important to separate cables to cylinders that are adjacent to each other in the firing order. If you will just keep in mind what the ignition system is supposed to do and what happens when one of the ignition units doesn't do its job, you shouldn't have any trouble diagnosing and correcting ignition problems.
And to help you in the diagnosis department, there's a handy troubleshooting chart in the reference book. It lists all the more common ignition problems and tells you what to test or inspect. You'll also find everything we've talked about today and more in the reference book. And when you're servicing the ignition system, use the information and specifications in your service manuals. On today's engines, there's no room for guesswork. And since that uses up all the time for this session, I'll see you all next month.